Now we have to be careful here because we've been talking a lot about partial and direct variation, but that's not what we're talking about when we say describe a scatter plot as going up. It could be that the scatter plot is going up and it's partial. It could be that it's going up and it's direct. I think these are both partial. Would you agree? So a similarity would be they're both partial. I think if you look at the trend here, they both will have, and I don't want you to draw this in, we're going to be doing this today. I think they both would have a general trend that looked like that, I believe. So we could say that a similarity is they're both partial. So that's how they are the same. What's another way they are the same? Somebody said going up. You said going up, didn't you? And remember, please, I'll just remind you, because we might have forgotten, I can't hear in one ear, so all my auditory stimulation comes from here. I need a hand so I know who I'm talking about. Yeah.
Both are positive?
Both are positive. So positive is the word we want to use for scatter plots that as one variable goes up, the other one goes up. So these are both positive, and looking ahead, they're both partial. I mean, we haven't really talked about drawing those lines in, but they are both partial. Who can come up with one difference? Kelly.
A is stronger than B.
Right, they have different strengths in terms of the correlation. This is a strong, well, we talked a lot about this yesterday, I think. It's a stronger correlation. I could certainly come up with a scatter plot that shows a correlation that's even stronger than that. But this is really pretty strong, I think. And if you weren't here yesterday, what we're talking about is how tightly the data is fitting in a line. I want to pull up something that I talked about yesterday just to remind you, and also for the people who weren't here yesterday. If you take a look at I have to open it. Give me 1 second. And this diagram kind of summarizes what we're talking about here in this whole unit. When you take a look at the cover page of your unit handout, we have these two kind of linear relations. What were they? Final mark in a course compared to the percentage of classes attended, and number of cookies compared to how much sugar you put in the recipe. And what we said yesterday is they are both linear. As one goes up, the other goes up. By the way, this would be partial, which means probably if you don't even show up for class, you're going to get something for marks. But anyway, that this type of relationship is perfect, we would say. I mean, it may not be perfect in that you can't necessarily measure a perfect amount of sugar, but the connection is nice and perfect. There's a formula. This one is, I don't want to say loosey-goosey, but it's less exact. Okay? So when we talk about strength, going back to this question, strength has to do with how tightly packed that data is to the line. The closer it is to the line, the stronger it is. And all I would say here is that this is weaker. There's one other difference, and I don't know if it's really that significant, but it's something we talked about. Does anybody know what one other difference is between those two scatter plots? Do you know?
One has an outlier.
One has an outlier. So this data point that's like the lone wolf that's out of nowhere, someplace it doesn't belong, is called an outlier. This one has no outliers. And all an outlier is an exception to the general rule. So maybe, here's a good example. Somebody said yesterday, and I don't remember who said the days from summer to fall and the temperature. You did? So let's do the opposite. Let's go from spring to summer. So we have, this is the temperature in degrees Celsius, and this is days after, I will say, March 1st. And what happens is as you go past March 1st, the temperature is probably going to start rising. If you like, you can change it to April 1st. I'm not a climatologist, okay, but you get the idea. It could be that these are for different towns, and this is a town where all of a sudden there was this freak storm that came in. Maybe a mass of cold air came in because there's a schnook someplace else, another part of the world gets really cold. Maybe that's what happened. So it's an outlier. So that's number one. Number two, you're asked to draw a scatter plot. Now, I don't want to spend class time drawing the scatter plot, but I hope that nobody had any difficulty doing this, right? You just plot the points. You have to make sure, of course, that the numbers that are in Y go on the vertical axis and the numbers that are in X go on the horizontal. Looking at these numbers, just giving us some practice for scale, the largest value of X is 6. So when I set up my scale on my horizontal axis, I don't think you want to do this. 1, 2, 3, 4, 5, 6. You can do better. The more of the graph you use, the better it is. So this is 1, 2, 3, 4, 5, 6. I think that's a better scale. What you don't want to do when you create a scatter plot, and you'll be expected to do so on the exam later this week, and on any assignment or quiz you have, you don't want to have this little tiny thing if you got a whole sheet of paper. What's my biggest one for Y? Well, it's also around 6. It's actually 5.5, so we could go 1, 2, 3, 4, 5. I'm going to move my Y over 6. So I'm not going to plot all these points. This is really the big part of this little mini lesson is how to set up the scale. But if you did, 6, 5 would be a point. So you would put a point here. And you don't have to draw this big blob of a point, but when you draw it for me on an exam or an assignment, don't just put a little tiny dot. I want to be able to see it. The reason why you might need to know how to do this is I might give you this data on an exam, this table, and ask you to describe the correlation. Positive strong, positive weak, negative strong, negative weak. And I hope you would agree, how many of you can see that this will be a positive-ish correlation? That the numbers, as X gets bigger, in general, Y gets bigger, doesn't it? Okay. But in order for you to see whether it's strong or weak, and I suspect it's going to be weak, but I don't know, you have to plot them. And I'm not going to plot them right now. Okay. B, describe the relationship. Is it linear or nonlinear? Well, it's going to be linear. Is it direct or partial? We've already had that conversation. You know what? It'll take me under a minute to plot these points. Let me get them plotted and we can talk about what it looks like. All right. 5, 3. 5, 1, 2, 3. 2.5, 3.5. 2.5, 3.5. 0.75, that's kind of an ugly one. 0.5. I mean, you can see it's positive, right? It's starting to take shape. 3, 1. Ooh, I'm thinking really weak so far. 5.5, 3.25, 5.5. 1, 2, 3.5. 3.25 would be here. 4, 5.5. 2. 4, 3.5. Can we agree it's positive? If it's negative, it's going down left to right. This is going up. You have to really strain your mind to see that, but it is going up. There is this band in here that looks like that. It is going up. Is it strong? No, it's weak. So it is a weak positive correlation. Is it partial or direct? Well, I think, that's a tough one. You could argue both ways. I think this kind of comes from the origin. But you agree it's not as simple as looking at a line? Okay, we'll talk about that later today. What else are we asked? What is the direction of correlation? Positive. What is the strength? Weak. Are there any outliers? Well, you know what happens here, everybody, is the correlation becomes so weak that it doesn't even make sense to talk about an outlier. How many of you, by a show of hands, would say that you believe this is an outlier? I might agree with you. If you said there are no outliers, I might agree with you. This is not a precise thing. We're looking at page 13 of your unit handout. And as I said, we're going to finish off the unit with this lesson. It has a few examples. You'll get some practice today with this material. Tomorrow, again, quiz or assignment. You may not know until you get here tomorrow, okay? And after you're done the quiz or assignment, you're going to get started on review material, which you'll continue to work on Thursday, so that Friday your exam is, you're good to go. All right. So this is called Scatterplots and Linear Trends Part II. I want to read through a couple of things with you. Even though the data in the scatterplots do not fall in a perfectly straight line, you can still use the scatterplots to make predictions. Okay? Are your predictions going to be as precise as, well, I need 1,800 grams of sugar to make my cookies? No, they're not going to be as precise. You're going to get a numerical prediction for these things, but we're just saying we think it's going to be around a particular value. The line of best fit, this phrase, means a line that best represents the data. Okay? We'll get to that in a second, and that's why you have rulers today. If I had a scatter plot, and I will draw one for you here. If I had a scatter plot that showed home prices, we'll say in Wetaskiwin, compared to the year. So this might be 2018. This might be 2024. You catch my drift here? I think you would agree, you know this even though you may not pay all your bills and buy everything for yourself. The price of stuff goes up every year. It's called inflation. So what you might find is that in 2018, of the 6 or 8 homes looked at, the prices might have been those numbers. I don't know what these numbers are. This number here might be $200,000, or it might be $100,000. That's not important. And then, 2019, you survey, you go back and you look at all the homes that were sold. There might be some home in 2024 that is really cheap because it's been gutted by a fire. I don't know. There might be some home in 2018 that's really, really expensive because the person who built it was rich and they put in gold handrails and faucets everywhere. I don't know. There are always going to be outliers. So do you agree that if I said to you, what do you think you're going to pay for a home in Wetaskiwin in 2025, you could look over here and answer that question? Would it be a precise answer? No. But you'd be able to say, I'm going to pay around this much in 2025. For a scatter plot of crop yield compared to the amount of fertilizer, you could look at that and you could determine what your yield in the crop in terms of maybe bushels per acre would be given a certain amount of fertilizer. You get my idea here? Well, it's not my idea, but you understand? Okay. So for each scatter plot, use a ruler to draw a line of best fit. Do not draw anything just yet. Don't get ahead of yourself. The first thing to note is you are not going to connect the dots. You're going to draw a single line. Look up here, please. I don't care what this is. There's a weird outlier here. Maybe this is... I think this was an example we used yesterday. Yeah. If you weren't here yesterday, what we're talking about here is a whole bunch of different gas stations, say in Edmonton. And that's why it's not in a perfectly straight line, because different gas stations charge different amounts per liter. This outlier on the axis there, what do we call it? A pump and run? Somebody came, filled up their tank, and took off. They didn't pay. So I'm asking you to look up here. Would you agree or disagree that this line represents the data? You would agree? No. I mean, think about it. If I draw that line, I'm saying that's the trend. What about this line? It's the right kind of direction, but it's not in the right location. What you want is a line that has the right angle and gets the data crowded around it as much as possible. And you want that line going down the center. So take a minute, take your ruler, and draw a line similar to that. Remember, you're not connecting the dots. It's not that kind of graph. You want to try to draw it so that you have just as much data above the line as below the line, and the angle has to be right. The other thing I will tell you is, as long as you have only, I'll say 2 or 3 or maybe even 4 outliers, you just ignore them. Don't worry about them. You draw your line of best fit. Are we okay with that? Okay. What about this one? What would your line of best fit be? Well, we do have an outlier right there. We're going to ignore that data point because it's an outlier. You can't base a conclusion or a decision using the pump and run person, right? You can't use the exception. I hope you would agree that the line is going to go down. I want to draw something, don't draw this, and tell you why this is wrong. The reason why this is wrong, even if I put it there, would you agree there are probably just as many points above that line as there are below, roughly? Yeah. But you don't want it angled like this. Are there just as many points over here as there are there? Yeah. You want it evenly distributed. So it's a hard thing for me to teach because what I'm kind of telling you is you just eyeball it. And I would probably say that if you drew your line like that, I think that's pretty good. See, here we're going to run into a problem because in a minute we're going to be finding the equations of these lines. So if I ask you on an exam to all draw a line of best fit and find the equation, I could get 35 different equations, and that's fine. They have to be close to each other, though. Okay, let's take a look at example 2. In a factory, bearings, which are little metal spheres, are produced. And due to machining imperfections, there's always going to be some that are defective. I think everybody knows this. When you're in industry and you're manufacturing things, some items get discarded because they're wrong. They're the wrong size. They have flaws in them. We call that defective. So the defective items are discarded. In general, the longer the production run, what does that mean? Well, maybe on Tuesday the production run is 2 hours. That means they turn the machines on and it works for 2 hours. Maybe on Wednesday, because they have more materials on Wednesday, the production run is 6 hours. Doesn't it make sense to you that the longer the machines are running, you'll get more items, but you'll get more defective items? Okay. Some of every group that you produce are defective, so if you produce more, you'll get more defective. And this is the scatter plot. So in this particular case, the production run is not given in terms of hours, it's given in terms of bearings. For example, on one particular day, when they produced 250 bearings, there were 5 defective. Are you with me on that? So somebody has kept track of this. Like on this particular day, I don't know what that is, maybe that's about 42 bearings, they had 4 defective. On this particular day, they produced 19 bearings and none were defective. It's not a perfect fit. But what we want to do here is determine the equation of the line of best fit. So we have to draw a line of best fit. I hope you're using a pencil, because what I'm going to ask you to do is draw what you think the line of best fit is, and you may have to erase it and redraw it. Okay? Are you with me? Okay. So take a minute, put your ruler down, slide your ruler around until you feel the edge of it is lined up where it should be. I might go as far to say this, as saying this, that if you felt this is an outlier, I can live with that. And if you felt this was an outlier, I suppose I could live with that. And by doing that, by taking those, in this case, 2 points that are kind of extreme points, they're further away from all the other points, it might help you see that the line of best fit is probably, now I may change the angle here, but it's probably something like that. I would probably move this up a bit. So by a show of hands, how many of you drew a line of best fit that's in the right neighborhood? Okay. It could be that the line of best fit you drew, you're saying is not in the right neighborhood, but you're being too critical of yourself. If you drew anything, how many of you had a line that went down more? That's fine. That's fine. You're going to get, if we use your line for the next part of the question, we're going to get a slightly different answer than if we use my line. All right? So we want to determine the equation of that. Is this, Vanessa, is this partial or direct? It's partial. And the equation for partial variation is y equals the slope times x plus the y-intercept. And this is a very difficult thing for me to teach because you all have lines drawn, right? And they're probably all different than mine. So when I go through this, I'm going to find my slope and my y-intercept and build the equation. You're going to find your slope and your y-intercept and build the equation. And we're going to get different equations. Do you understand the weirdness of this example? If you want, you can take a minute and try to draw my line and use it if you want to follow along precisely. Okay? Are you guys with me on this? Okay. So I'm looking at this, and I'm going to start with the y-intercept, which is the y-coordinate of where the graph crosses the y-axis. And, you know, part of me, you know what part of me wants to do? Is this. Is just move the line so that it's at 1 and I can call it 1. I'm not going to do that. I'm going to say the y-intercept, my y-intercept, is about 0.9. It's probably even closer to 1 than it is 0.9. But I'm going to go with 0.9. Now, how do I find my slope? Well, I need to take rise over run. So I need to draw a triangle here. And it's not going to be as simple as like the cookie example or those other examples that were direct or partial, because my line may not have points on it that I know the exact coordinates of. But I'm going to go with from here to here. That's going to be my triangle that I use for my slope. Now later on today you'll get some practice doing this on your own. But for now we're just following along here. My rise, let's take a look at this very carefully. This is at about 4.25. Nope, it's at 4.5, isn't it? Because this is 4, this is 5, this is 6. So that is at y equals 4.5, and down here it's at 1. The rise is 4.5 minus 1, which is 3.5. My run is from, I'll say 10 to 200, which is 190. So I'm going to have 3.5 over 190. How many of you are doing this, but you have different numbers because you're going with your line? Okay, just hang on, because there's a test here that we're going to see at the end whether you got a pretty decent answer. Okay, so don't worry about the numbers being different. That means my equation is y equals, well, we might as well calculate this. 3.5 over 190. Let me grab my calculator. It keeps popping to my other monitor. .5 divided by 190 is 0.018, and I think that's good enough. We could go 0.0184, but I think 0.018 is good enough. So my equation will be y equals the slope times x plus my y-intercept, which we said was 0.9. Now, you've already had practice in finding equations of lines. You've done that with partial variation. That's where we ended a couple of days ago. So that's the equation. Let's take a look at the next part of the question. Let me grab this because I'm going to be using it. The next part of the question says, how many defective items do you think we would get? Here's the prediction part. How many defective items do you think we would get if you had a run of 68 items or a run of 400? Well, think carefully. I want everybody to think on this. Is this a number that's going to go in for y or x? Right? It'll be x, because you look at the graph, this is how many we produce. This is the production run. You look at the graph and the size of the production run is on the horizontal axis. I could have put the letter S in for x, for size of production run, and N in for y, number of defective. But the bottom line is this question becomes easy. This is going to be the number of defective is 0.0184 times 68 plus 0.9. That's it. We have to calculate that. So I need to take 0.0184 times 68, and I'm going to add 0.9. And I get 2. Now, I don't get exactly 2, right? But you understand we can't have 2 point something defective items? Are you with me still? Okay, I'm getting 2 defective items. How many of you did this with your own equation? What did you get, Ryan?
I got 11.192.
You got 11. So your graph is really different. Let me take a look at your line. So you drew your line up quite a lot, which means you have that y-intercept that's greater.
Yeah.
That's fine. Okay? When I mark something like this, I'm going to be looking at your graph and your work. If I want everybody to get a precise answer, I will put the line in myself. Shanna, did you say you did it with your own line?
Yeah.
What did you get?
2.086.
2. So we're in agreement. We kind of drew our lines the same way. Who else did it with their own line? What'd you get? 2.39. 2.39.
I got 2.11.
Okay, so you know what? I want to check your calculations, because if you did it right, it would be right, but 11 seems high. So I'm going to come back and you're fine with that?
Yeah.
Okay. I'll come back and I'll look at yours in a second. It could be that you just put a number into your calculator wrong. I think if you do a half decent job, we should probably be getting 2 or 3, maybe 4. Okay. Let's try this now, 400. Well, all we're going to do is the same thing. Y equals 0.0184 times 400 plus 0.9. Let's see what we get this time. So I'm getting 8. What are you getting?
6.9.
7.
I got 8.
8.
8.2.
8. Anybody else? 8 and 9. That's pretty close. Okay. So I'm just going to go 8. Defective. Yeah, I'm going to have to check that calculation. We'll see. Don't worry about it, though. If there were 11 defective items, what is the likely size of the production run? So is this 11? Let me write out the equation. Y equals 0.0184 x plus 0.9. That's my equation. Is that 11 going to go in for y or x this time?
Why?
Y, because that's the number of defective. So we put 11 here. And everybody should know how to solve this equation. You're going to subtract 0.9 and then divide by that 0.0184. So if I subtract the 0.9 first, can you people out there with the calculators let me know if you get 10.1? When I subtract the 0.9 from 11? Good. This is equal to 0.0184x. Well, now I have to divide both sides by 0.0184. Let's see what I get. And again, a few of you have stuck your neck out in a good way and said, I'm going to use my own equation. So I want to know what we're going to get with the other equations. What do we have? 10.1 divided by 0.0184, 500. See, you know what I almost said when I looked at that number? 550. Because it's not a precise science here. I'm going to say about 550 bearings were produced. Shanna, did you get an answer?
Yes.
What-
682.
682. And what we're going to discover is as the numbers get bigger, our numbers are going to start getting further away from each other. Do you have one, Dylan?
I got 750.
7,
Or
551? So somewhere between about 550 and 650, around there. All right, I have one more example I think that we want to take a quick look at. But I'm going to change my mind. I mean, I'm looking at the clock here. There's about 25 minutes left in class. I will just ask us to do the following with example 3 together, and then we'll move on and get some practice for you. What question 3 is asking you to do is find the equation of the line of best fit for these two things. What this is showing is fuel economy compared to the weight of the vehicle. So this fuel economy is telling you how many kilometers you can travel per liter of fuel you burn. So if this number is up higher, that's good. It's cheaper for you. But what happens is, as the vehicles get heavier, the fuel economy goes down. And there's a difference between highway driving and city driving. Highway driving, you get better fuel economy because you reach a cruising speed and you just drive. City, you're slowing down, you're stopping, you're speeding up, you're wasting fuel. What I want you all to do is draw the two lines of best fit. You got them drawn already? Okay, so I would like you to draw the lines of best fit, please. And listen, you guys, if I'm standing up here going, if I'm doing that, it's natural for you to be doing that. But at the same time, that's not an excuse for you to put your ruler down and say, oh, that's the line of best fit. Clearly, that's not the line of best fit. Of course. So, how many of you had ish lines like that? Okay. So you should be able to determine the equation by finding the slope and the y-intercept. You would need to extend these lines so you could read the y-intercept. In this case, I might have to estimate the y-intercept. And if you wanted to find the equations of both of these lines, don't forget that your slope for your equations will be negative because it's going down. And then you could make predictions. If your vehicle had a weight of 1,100 kilograms, what should your fuel economy be in the city or on the highway? Would you agree, by the way, they're both negative correlations? And city driving is a stronger correlation? It isn't the steepness of the line, it's the tightness of the data. And city driving, the data is closer to the line. It's not as spread out. So that's it in a nutshell. All I'm going to ask you to do for tomorrow is number 3 and number 5 that are on page 33 of your handout. It's going to involve you plotting data, possibly drawing the line of best fit, finding the equation of the line of best fit, and then using the equation to answer questions.